All right, so if you'll recall from yesterday, we had figured out how to neutralize the ammonia. We were going to use ethanoic acid solution. Problem is that we'll leave acetate ions in the solution, okay? And so what we're worried about now is that a high concentration of acetate ions can be irritating to skin and mucous membranes. Obviously that would cause some problems for all the little fishies we've been struggling so hard to protect. We need to think about how can we take acetate ions out of solution. Now, we know that acetate ions and silver ions are essentially, they will react and their solubility is very low. So we would consider that insoluble. Our simple solubility rules would let us know that acetate and silver ions essentially precipitate out. But we want to add just the bare minimum amount of silver ions to remove most of the acetate ions. And it turns out that all of that solubility stuff that I taught you, that simple solubility rules, which are sort of good early predictors of what's going on, belie a much larger reality, a much more complex reality of how solutions behave, how solids behave when they dissolve or precipitate out of a solution. In fact, all of those things are generally considered equilibrium problems. And so much as we've talked about Ka values for an acid dissociating and Kb values for a base reacting with water, we want to define an equilibrium constant for a solid substance, a solid ionic compound, breaking apart into its ions as it dissolves into water. And we call that KSP. The SP stands for solubility product. Now, make that a little easier to see there. So a solid ionic compound breaking apart. So our silver acetate, breaking apart, dissolving in water, okay, to form the silver ions and the acetate ions. Of course, we're changing this from being a, one-directional equation to being an equilibrium situation. And so that's where we have the KSP. KSP is defined as a solid breaking apart into its ions. We always write the KSP the same way, regardless of what reaction we're actually doing. Just like when we're dealing with Ka and Kb. A Ka is always an acid breaking apart. Solubility is always a solid breaking apart. So the KSP, the solubility product for this reaction, would be, the expression would be the concentration of the silver ions times the concentration of the acetate ions. Why do I not put the silver acetate on the bottom here? It's a solid. Solids concentrations are fixed. We don't have to worry about their influence in the equilibrium expression because their molarities are constant values. So, the solubility is one of the ways we typically express how much silver acetate will dissolve into a solution. And in fact, the solubility of silver acetate is 4.4 times 10 to the negative fourth molarity. That is, I can get 4.4 times 10 to the negative fourth moles of silver acetate to dissolve in 1 liter of a solution. We want to take this solubility and use it to calculate the KSP value. Because the solubility is telling us at equilibrium how much of this stuff breaks apart, how much of the silver acetate breaks apart. In other words, if we were to think about this as an ice diagram, I know that I have some amount of the silver acetate. We don't really care about how much we have because it's not part of the KSP. But I start with 0 of the silver and 0 of the acetate. What I know is that from this sentence right here, the solubility tells me how much silver acetate broke apart. That's essentially like the change value. It's how much of the solid broke apart, which will give me the value for the silver and the value for the acetate, right? I'm going to get those two values from the solubility. Once I have those values, because I started with 0, I can solve for the KSP value, right? I'm going to take that same equation and I'm going to substitute in the concentrations of silver and acetate. The solubility product constant, the KSP for silver acetate, is 1.9 times 10 to the negative 7. That's simply multiplying these two values together. Question?
Wait, so does the solubility of silver acetate, is that set? Because wouldn't that depend on how much you have of it? Or how much
No, the concentration is fixed by this equilibrium. It would change with temperature, but not with how much, not what volume of solution you have.
But isn't that how much of it's dissolving? So you're the same.
Well, this is, remember, this isn't how much is dissolving. This is the ratio to the moles to the volume of the solution. If you wanted to calculate how much, what mass would you need, you'd have to know what volume of solution you were trying to make. And you can make solutions that are less concentrated than this, but you can't make solutions that are more concentrated than this. If your ratio, if your product of the silver ions and the acetate ions gets over this number, okay, or over this number I should say, then it will start to precipitate out. It will start to form a solid. But this solubility, that's the maximum solubility you can get at a given temperature. Changing the temperature changes that solubility because it changes the K value. Questions, Hannah?
But you don't include the solid.
Solid concentration of solids doesn't change.
How does it not change if it's dissolving?
Well, the dissolved part of it is the ions, right? That's the part that has been dissolved. The rest of this solid is sitting in a layer at the bottom of the container. It's not dissolved. It's separate, physically separate by being a solid instead of being dissolved into the liquid. That's different than, say, when you take sugar. Sugar, we start as a solid. It doesn't break apart, but each individual sugar molecule breaks off and dissolves and floats into the solution. Silver acetate will not, as a solid, float around in the solution. It sits at the bottom, it separates out, it clumps together.
What if they tell you, like, you put in a certain number of grams of solid silver? Does that not include the ions that are going to dissolve?
Well, it depends on how it depends on how they phrase it. If they say we added X number of 10 grams of silver acetate to a 10 liters of solution, how much dissolved? They could ask a question like that. They could ask how much was, then we filtered it out, how much was left. Those are kinds of questions they could ask. You would take the solubility times the volume to get the moles that dissolved, and you'd subtract that moles that dissolved from how much you added to find out how much is left as a solid sitting in the bottom and how much is in the floating around in the solution as separate ions.
Why does it all? I remember.
Some of it won't break apart. What happens is we form an equilibrium between the silver and the acetate sticking together and turning back into a solid versus the silver and the acetate breaking apart. So we establish this equilibrium. And why the equilibrium point is where it is depends on a number of factors, a lot of which we're going to talk about when we come back from spring break.
If they don't specify, do you assume that you started with 0 products?
Yes, if they don't tell you you put it in, you start with 0. They will do that, and we'll see that in a few slides, where we're going to do a problem where they say we'll have some initial concentration of some of these, and we'll have to do the calculations. This is a way where this very common solubility value, you can use it to find out KSP. The key thing to remember is that the solubility is the equilibrium value. They're telling you how much broke apart, what the concentration of this stuff was that could break apart. Okay? So, typical type of problem is to now take that same idea and reverse it. If I have the KSP value, can I find how much would dissolve? I want to reverse this process and say, okay, now I've got the concentration. Okay, I've got an initial concentration. I know the KSP because we just got that. I just gave it to you. Now we want to do an equilibrium problem and say, what concentration, so this is the concentration of the acetate ions, just the acetate ions. The question is, how much silver ions, what concentration of silver ions do I need to just start precipitating, to just equal that KSP value? So let's take a minute and do this problem. All right, so you got this equation, right? You've got the equation. You know what the KSP is. What they're asking you here is, hey, if this value is 0.005 and we know what the KSP is, what does the silver ions have to be to just hit the equilibrium? So we want the KSP is equal to X times 0.005, and we know the KSP value, 1.9 times 10 to the negative 7. Where did I get that? You recalculated it, I calculated it on the last slide.
Would it make more sense for this concentration of silver ions to just be the same as the concentration?
Well, if the concentration of the silver ions was the same, what would this value be?
Well, I know, but like, I'm not thinking about that right now.
So here's the thing. You got to remember what problem we're talking about. We're not saying that we put the silver acetate and it broke apart. If you are talking about silver acetate breaking apart, yes, then those two values would be the same. But the situation we're describing here is that we have a solution that has a concentration that has some acetate ions. Probably that came from like vinegar being neutralized. Ethanoic acid reacts and gives us acetate ions. So the question we're asking is, how much silver ions do I have to add somehow by having another mixture? How much silver ions do I need? What concentration of silver ions do I need so that the acetate ions will just start to precipitate out? So the acetate ions, they're very soluble in water. Okay, guys, put it away because you can't be quiet. Sorry, say it again. No, the acetate ions aren't splitting apart. What we were talking about splitting apart was silver acetate solid. That's what we did last slide, right? So then we had like vinegar. Vinegar reacts, put it in water, and we get hydrogen ions and acetate ions. So let's say we had a vinegar solution and we know there's acetate ions in there. We want to take the acetate ions out. We want to react them with something to remove them. Well, I can add silver ions, and if I put silver ions in there, they will stick together with the acetate ions and form a solid and sink to the bottom and come out.
Isn't that forming?
Yes, this is the reverse reaction. Now, the reason why we don't write it as ion to solid is because that's not what KSP is. KSP is defined as always being written as solid breaking apart. And we want to use this KSP value because it defines this equilibrium. And since equilibriums happen forward and backwards, it doesn't really matter which way we're talking about as long as we know what this value is.
So then are we precipitating silver acetate, not acetate ions?
Yes, we are forming silver acetate as a way.
Precipitate acetate ions, because that's not what.
We are. The acetate ions are precipitating out of the solution in the reaction with silver. This is a common sort of way to say, hey, I want to take the acetate ions out. And so we're causing them to form a precipitate with the silver. Okay? So the question is, how much silver do we need to add to get that to happen? No, we're finding out the point where it would just start happening. Well, you can't really get to all of them. Right. Theoretically, yeah. But it's always going to be in equilibrium. And we'd have to throw this value up really high to get rid of all of them. So yeah. Okay? So we solve for x, and we find out once the silver ion concentration hits 3.8 times 10 to the negative 5, then the precipitate would start to form. What's wrong? You guys have a question? No. Okay. Okay. So the fundamental idea in this problem is we've got some acetate ions. We want them to react with silver ions. What concentration of silver ions do we need so that they'll just start reacting together to form the solid? Now, you have to remember this is an equilibrium. The equilibrium defines the relationship of the forward and the reverse reaction. For the reaction to push to the left, right? For the equilibrium to push to the left, I have to get to a value that's at least equal to the KSP. If the ratio, if this Q, right? Think about the Q value. If I multiply these two together, and my Q value is less than KSP, the reaction would shift to the right. That is, I would try and break stuff apart, but I don't have any, so it's not going to form. To get it to push to the left, my Q value, my reaction quotient, has to get higher than KSP. So I want to find that point where it would just start to push to the left, where these two concentrations would force the equilibrium to the left. That's a very typical kind of question. I don't think so. I don't think so. That's a tricky question. You will see there will be some sort of multiple ions being removed. We're going to see in a sec. Yeah. Yeah. We'll do that. We're going to do that as a problem in a sec. Yeah. Yeah, you can't just flip the equations around because that inverts the K value, which is why when somebody gives you a KSP value, you have to write the equation the way a KSP equation is always written, because otherwise it won't match with the number.
And then for other equilibrium values, it's just write it based on the order of what they gave you in the reaction.
Yeah, and we don't care what's the order within the reactants. We care what are the reactants and the products. If I flip those around, that inverts the equilibrium constant, and it's a different number. And you could do that. If I flip this around to write silver plus acetate to form silver acetate, then this value would be 1 divided by, okay? Right, so it would be 1 over all this stuff. Right, the solid is not included in the equilibrium. That doesn't mean you can't invert this. The number would be 1 divided by all this stuff. Or you could just write all these to the negative 1 power. That would be the same as inverting, if you wanted to reverse the equation, which I don't think you should do. No, generally KSP means solids breaking apart. Okay, so looks like we might be able to take out the silver ions, okay? Or maybe we could think about neutralizing the acids and bases in a different way, okay? Turns out that a little bit later on there was an accident near the pond, and a truck spilled whole bunch of sodium carbonate into the pond.
Oh no.
It's a terrible tragedy. As you can see, there was quite a large fish die-off. Those are all fish. So, looks like the fish are being poisoned by the carbonate. So now we have carbonate and acetate in the pond. Well, there's still some fish left, or we want to clean the pond up and then restock with new fish.
How sure are we that's not a fish truck that spilled?
It could be, you're right. That could be what happened, a fish truck that spilled. So here's the situation I want you to think about. We had the KSP for silver acetate. The concentration of acetate in the pond at the moment appears to be 0.001. I'm giving you the KSP for silver carbonate. It's 8.1 times 10 to the negative 12. The concentration of carbonate in the pond appears to be 0.005. I want to take, a sample of the pond water, and I want to remove the acetate and the carbonate. So what I'm going to do is I'm going to take and I'm going to add silver ions a little bit at a time, like a titration. I'm going to add silver ions by adding, say, silver nitrate solution. Silver nitrate is a good source of silver ions, highly soluble. So basically a solution that has silver ions. I want to know, first of all, which one of these is going to precipitate out first, and what concentration of silver ions will I need to cause the precipitation of each of the different ions, to precipitate out the acetate ions, to precipitate out the carbonate ions. So same sort of question I just asked, except now I have two different ions in there. Okay? So, which one of these do you think is going to precipitate out first? Why do you think the carbonate? KSP is much lower. That's a good first order check. Smaller the KSP, the lower the concentrations that you need to get precipitation started. Now, it's not quite exactly that simple, because we do have to think about in this case we are going to have some coefficients on our equation, but it's a good rule of thumb. How do we go through and figure out what concentration of silver ions we need? How do we just do that in the last slide? You want to think about the KSP, what the KSP equation is, and what the concentration of the anion is, this negative acetate or negative carbonate. So take a sec. You want to start out probably by writing down the chemical equations for what are going on. So take a sec. We're going to have two separate precipitations. I'm going to have an acetate precipitation, the one we've been talking about, and the new one is a carbonate precipitating. Carbonate, silver carbonate is this. So carbonate, which you should have memorized, CO3, -2 charge. So take a minute and go through and see, just going to do the same calculation sort of twice. Calculate the concentration of silver ions to precipitate out the carbonate silver ions to precipitate out the acetate. All right, so let's take a look at this. Let's do the one we're familiar with first. Okay, acetate. We know what the KSP, the chemical equation, silver acetate breaking apart. We also have a second reaction taking place. Very important to know what the reaction is because this coefficient of 2 here is important. Okay, this coefficient of 2 is important. So, for the carbonate, what's the KSP equation? KSP equals Ag squared times the concentration of the carbonate. And for the acetate, the KSP equation, we already know, silver times acetate ions. We know the concentration of the carbonate ions. It's given to us in the problem. We know the KSP value given to us in the problem. Substitute, solve for X. So when the concentration of silver ions hits 4.0 times 10 to the negative 5, silver carbonate will start to precipitate out. I took 8.1 times 10 to the negative 12 divided by 5.0 times 10 to the negative 3rd. Okay, guys? Shh. And then I took the square root of it. When the concentration of silver ions gets to 4.0 times 10 to the negative 5, the silver carbonate will start to react, the silver and the carbonate will start to react and form silver carbonate solid. That's the point at which the silver carbonate will start to precipitate out. Let's find out how does that compare to the silver acetate. Same process. I know the KSP value. I know the concentration of the acetate. I solve for X. So which one of these precipitates first? Carbonate. You need a lower concentration of silver ions. The silver ions will start to precipitate with the carbonate first. We keep adding them. The silver carbonate will precipitate. Eventually the concentration will go up. Once the concentration of silver ions hits 1.9 times 10 to the negative 4th, then the silver acetate will start to precipitate as well.
So even though they're like happening at the same time, we don't need to worry about the fact that some of the silver is going to making that one, so would it not be...
Right.
So it's not like once we get to 1.9...
Well, once we get to 1.9 times 10 to the negative 4th, this stuff will start to form. Yes.
But when it takes longer...
But it will take longer because a bunch of the silver ions are being removed by this equilibrium. Yes. So how much do we have to add is a different question than what concentration do we need to get to. Those are different questions.
Can you figure out how to do that? How to figure out how much more we need to add if some are precipitating with the carbonate?
No, I don't think you'll need to do that. What you will need to do, however, is answer the question, what concentration would the carbonate ions be at when the silver acetate begins to precipitate? In other words, reverse this problem a little bit. Say, hey, if the silver ion concentration is this, what would be the concentration of the carbonate ions? So you do the same process, plug it in and solve. So, what's the concentration of silver ions that they're asking me to think about? 0.9 times 10 to the negative 4th, because that's the concentration of the silver ions when silver acetate begins to precipitate out of the solution. So the question is, what will be the concentration of carbonate ions when acetate begins to precipitate out of the solution? So take a second, do it.
Wait, so are we using the KSP link or the...
We know the KSP, that's not going to change. We know that. We know the concentration of silver ions. We're trying to find the concentration of the carbonate. So we just reverse that a little bit. Take a couple of minutes. All right, so we know the equilibrium. We're dealing with the carbonate. The KSP is the same, but now what we're looking for is the concentration of the carbonate ion. And we have the concentration of the silver. The concentration of the silver is 1.9 times 10 to the negative 4. That's the concentration at which acetate starts to precipitate. So we know that if the silver concentration is 1.9 times 10 to the negative 4th, the carbonate concentration would have to be 2.2 times 10 to the negative 4th. Now here's a question you could answer. How much carbonate has precipitated out once you've got to this value? So in other words, what's the difference between what you started with and where you are now? If you took the difference between those, that would be the change in the molarity times the volume of the solution would give you the amount that had precipitated out, the moles that had precipitated out. It's not a real question. I want you to realize that by looking at the difference in these concentrations, you could find out how many moles have actually precipitated. So, KSP, fundamentally, there are only two new things about this. One, we've defined a new type of equation, solubility product equations, solids breaking apart with new equilibriums. The second thing that's sort of new here really is the idea that we know or we measure the solubility of a substance. And the solubility is essentially how much of it dissolves into the water. What is the molarity of the stuff you can get to dissolve? And that typically we use that to find KSP values, because the solubility is how much of the solid broke apart. So we can use that to find the equilibrium values for these guys. That was the first thing we did. Other than that, the equilibrium problems that you'll see about this, because there will be some equilibrium type calculations with ice diagrams and everything, are the same ones that we've already been seeing. They'll give you an initial concentration. They'll ask you to find some final concentration. There'll be X's. It's the same process. Okay? We're done. We can control everything we need to. We can get lots of happy fishies. Okay? Until the next disaster. She's training the fish to go through a hoop. Yeah, you can actually. You can. Percent ionization is the amount that broke apart, the amount that reacted, divided by the initial amount you started with, times 100.